Thank you. Thank you. First, thanks the organizers to give me the opportunity to give this talk. It's a very particular the talk after Nick. What can I do? From it's really going to be a very you should lower your expectation. That's good. So secondly is really I want to. It's a conference to celebrate Alan's 60th birthday. So I try to remember when I was first time meet Alan, but for sure we met when he as an assistant professor at Berkeley. That was 1990. But before that, I also met Alan at Cornell. That time he came back from the CELFAX. He briefly stayed in CELFAX, is right. Nick was there, and we were working on the LA pack. This was around 1988 and 89. So we had this every few months. All the developers get together and doing the debugging and developing the code, etc. Cornell, the supercomputing center, hosts a bunch of them. I remember that times, if I have time, I can report a client Alan made. What's the client is, he came back from the CELFAX. So remember you the street name tag you took down from the friends.
Well, Nick can tell you more about that.
Yeah, Nick can tell you about that.
My daughter still has illegally acquired.
Illegally acquired, that's what I was. So I got very excited and impressed by Alan. Besides,
oh, I scored it too at that point.
Yeah, you took it too, and then we had a party at the Nick's house. You as a gift, you unwrapped that. Nick, that time your daughter just was born.
Maybe we should tell everybody quickly that I think the statute of limitations is out.
Yeah, it's all exactly.
So I don't know, Nick wants to tell the story, Nick just had his first daughter, Eigenvalue-dependent, named for Rue de Javel Street in Paris. And a friend of mine from Fairfax, Stefan Dodé-Kilvé, and I, we actually went with tools to Rue de Javel. You know, it was maybe 2 in the morning, and we were right past the police station. I'll never forget. And I was very nervous. But we found a truck, parked on the sidewalk as it was due in Paris, blocking the street sign, and we took it down. And I smuggled it out of France, and very nervous going through security. But once I went through security, I was very happy.
Yeah, it's already off the Statue of Liberty, the procedure.
Emma still has absolutely.
Yeah, that was my most very vivid memory and to interacting. Of course,
that's
when
my entire life.
now it's not secretary anymore. So, and afterwards, of course, when Alan was at Berkeley and doing the internship, I usually spend a few months during the summer months and at the Berkeley, and we also interacted. We had a lot of good times and hunting for Chinese meals frequently. The other things I also are very grateful in the sense of Alex talked about the advice, and in a sense, Alan and I graduated roughly at the same times. So I studied after I did postdoc at NYU's and also briefly at Tennessee. I studied a faculty position at the University of Kentucky. I started to teach in the calculus, etc. So, and once that was quite a few years down the road where Alan is already at MIT. And then I got very depressed in the sense of trying to push the teaching the calculus, teaching the linear algebra. I just find that the students are very not really ready for those. They even don't have a basic. I made quite a few assumptions about some math from the high school. I made an assumption they should know this, like trigonometric, etc. So I sort of share my thoughts with Alan, say, you know, it's very hard to teach us. So Alan words is say, it's okay, it's the same at MIT. So that's really boosted my morale. It's fine, I'm teaching the same kind of the challenging of Alan, etc. All right, so anyway, let's back to the object of my talk. And so in a sense of, we know that through the yesterday and today we'll continue, and Alan did lots of fundamental work in all sorts of fields in math and computing, and particularly in the linear algebras of that. So it's a very natural question is I would ask is when and from who Alan first learned linear algebra. Anybody know? Exactly, John knows that. Exactly. Here is the all reviewed that. So in the first edition, but of course the book existed for a long time as a lecture notes, but officially published in 1997 as the first edition. Here is the first paragraph of the preface of the first edition. That's read. The book is based on the lecture course designed for entering the graduate students and give over a number of years at the Coulomb. The course is also open to qualified undergraduate students, and on occasion was also attended by talented high school students, among them Alan Edelman. I am proud to have been the first to teach him linear algebra. So now you're just counting. Alan is, I did some Google. I went to this high school. It's closed already. It's no longer.
The building is still there.
Yeah, the building is still there, it's etc. And Alan, according to yearbook, I couldn't find a year photo. It's need to pay there, but I don't know even paid. I can get that. But anyway, I did not go through. So Alan was a class of 1980. So now you can calculate in the year. So when he started learning linear algebra, why he's so better than many of us. That was very impressive. By the way, this.
The 14th Street line. One subway token was all of it.
You can guess. He graduated high school at 17, and so probably 14, 15, and whatever, I don't know. So this high school is very impressive. Among the alumni is including this Howard Schultz. He's the CEO of Starbucks. Remember that? So it's very fitting of that. Of course, in the academic, like Ren-Cang of Berkeley. So Checker might know that he was a dean of UC Berkeley Engineering School. Very impressive. But anyway, so today, for the rest, I think I already killed most of my talk. So I will talk about this one particular work. Many of you probably also know that. And it's, besides the Julia, this survey article, which surpassed this article, it's the most cited work of Alan. Number one, according to Google Scholar.
The Julia paper is now constant.
Exactly. This is now on the number 2 list. But it's a very big, long paper. So I think it's already off the Science Journal standard. I don't know whether they are still allowing us to publish of a paper at 51 pages. Yeah, it's already that. So of course, here is a paragraph. It's a very groundbreaking of the paper and inspired tons of the work. And because number one, the richness of this paper itself, and I'll cover of course, the mathematics study from differential geometry. Yesterday, Stephen, his calls to talk about say it with matrices. That's exactly this paper, the spirit. Differential geometry was in terms of matrix characterization and practical. And also tons of the new algorithm development. It developed the new methods and unifying the tons of the different types of the algorithm in the fields, etc. So this is, as I say, that many of you probably already know that. It's become a sort of a must-read paper for any of the students like and to study, work with me, and etc. It's a very, very standard of that. So this was a couple of days ago. This is the citation number according to Google Scholar. Today, this morning, I checked. It's already 3,114. It's a 3 more citation. It's sort of like a stock price. So I'm definitely going to continue buying these stocks. Copy it goes down on that. So anyway, so back to the my talk, of course, completely inspired in a certain sense, try to mimic what Alan did in that paper. In the sense of back to that paper is unifying the theory and say it is using a matrix because also I'm my primary working in the numerical linear algebra, and we would like to say everything in the matrix and beautiful matrix eigenvalues, singular values, etc. So this is number one. Number two is that in the geometry, to understanding things of that geometry, as you probably know, Alan, throughout his career, he wrote tons of papers trying to explain what's the geometry things and going of that. So in the end, I will mention another his more recent papers. So But of course, I'm going to talk about one particular province in this talk, in the sense of is to try to maximizing the finite sums of the composite functions, in the sense of this is you have lots of the function phi I here. You, for simplicity, I assume some convexity and smoothness, etc. But for the presentation, otherwise you can make the, if it's non-smooth, if you have a certain Lipschitz condition, etc., you can generalize that. So composite in the sense of they are each of them is the elements of this so-called radial quotient, or otherwise you call it bilinear form. And the objective is how to maximizing such a type of functions on a complex domain, complex vectors. So it looks very sort of a standard. For example, a lot of machine learnings, etc. They talk about this. The number of the function phi I here can be small numbers later on. For example, like in numerical radius calculations in polynomials optimization, etc. The m is pretty small. But if in a machine learning setting, etc., like doing the discriminant analysis, etc., so m could be very large, and people also sometimes call it empirical risk, of something estimation. So this is basically the objective functions or objects of my talk. Would like to today the rest of this 10 minutes or so focusing on that, and so. Of course, there's another sort of a dual or another associate form is I would also consider this types of nonlinear eigenvalue problems. But I put a NEP, but put a little v there in the sense of this type of nonlinear eigenvalue problems. It's more depends on the nonlinearity, not depend on the eigenvalue like Alex talked about yesterday. But it depends on the eigenvector. As you can see, this general form of this, you have a nonlinear eigenvalue problem, but this matrix H here depends on the vector X you are looking for. Of course, to associate this today, we were just focusing on particular of these forms in the sense of you have all the matrices, but you have functions and associated within this, and then you sum of all those type of combinations, etc. Okay, so this is basically of that. So naturally, you will ask, what's the relationship between these two eigenvalue, two problems? One is on the optimization problems, the other is on the eigenvalue problems. Of course, this eigenvalue problems and optimization are in this type of form. Simplest problem we all remember is the type of like a Coulomb-Fisher min-max principle. Because all the eigenvalues, etc. So we ask a similar type of question. Is that connection between these two? So of course, we need to make assumption between these two functions. We assume one is the derivative of the other or antiderivative of the other. And the first things we can review is so-called variational principles. Namely, is that if you have eigenvalues, if you have a vector optimizing this, and you can show it's also eigenvector of this, and vice versa. And of course, there's some other caveat in terms of because this is a nonlinear eigenvalue problems, and you need to properly define what's the eigenvector stability, etc. And also optimization problems, of course, we talk about a local optimum, etc. So therefore, first is try to say that we can, from these two different types of problems, but they have a strongly connection. But of course, this connection is just immediately generalizing of what's the well-known, the standard textbooks of that material. So if you try to maximizing these radial quotients, we know that the maximum and the problem equivalent to eigenvalues of these problems. That's number one. Number two is that from this, of course, you often optimization problems, because you make assumption about a function's continuity or boundedness, etc. You know there exists in the optimum or global optimum even. But in this case, of course, from this connection, you can also derive in terms of the existence of the eigenvectors and eigenvalues for this type of nonlinear eigenvalue problem. The third is a little bit more subdued in the sense of in quite a bit of the applications, so a lot of functions, fx defined here, the matrices earlier is in the symmetric or in the real form. But over here, we can talk about more generally on a complex domain. And in this case, we can show in this setting, and both are the same. Although this naturally, in terms of format, they looks very different because one is on a complex domain, the other is a real. But in this case, we can show they are really so the same. So therefore, we can have a unifying formula or algorithm to treat both cases. So that's what we will show you an example later. Okay, so this is basically of the, you might call the theory aspect. So we really established the connection between these two types of that. Of course, just like we're doing a radial Gaussian optimization, etc., is converted to solving the eigenvalue problems. Similarly, within this so-called variational principles, so we can directly tackle this nonlinear eigenvalue problems of that. Of course, for this type of nonlinear eigenvalue problems, is the standard gateway method is the so-called self-consistent field iterations, or SCF iteration. It's sort of like a power method for linear eigenvalue problems. Everybody knows that. So what this algorithm is extremely simple. So that basically you're looking for x and lambda to satisfy this equation. So what you do is that you study an initial guess, and then you plug it into these matrices, and then this is become linear eigenvalue problems, and then you just keep looping. So generate of that. So this is a very simple of so-called SCF iteration. I think its names is started in chemistry and etc. in the earlier 50s, and so. Because this is also I should also mention that this is entirely this approach I'm talking about today is through the NEPv, etc. It's also in a very earlier inspiration in Allen's that paper in 1998. That was totally has 10 different applications and the types of problems listed there. And one of them is the so-called electronic structure calculation. Of course, that time was a physicist, of course, chemistry are very well known to tackle this type of problem, but very few of people like me or people in numerical linear algebra problems look at this because of that. But that paper made them very clear, and afterwards, this is basically all these types of the algorithm and etc. But anyway, that's another. So this is basically the gateway method for solving that. So the second is an algorithm. You naturally ask these two basic questions. Number one, what this algorithm really does, or what's the SCF really does? So of course, show me geometrically. That's the Allen will always ask you, say, what is it really does? Show me geometrically. What's that going on that? Second, of course, consequently, you want to make sure that this simple recursive iterations and eventually will convert into the eigenvectors or whatever you wanted, and etc. So this is the two fundamental questions I tried to briefly. So the first is that we can rewriting for this particular province, and we can rewriting this province in another form in the sense of if you're doing the change of variables, so we define this new variable y is a vector, okay? So therefore, you can rewrite it because inside of each of that, this is each of the components, y1 to ym. So you can rewriting this province as an optimization set. This set is nothing but is the so-called joint numerical range. Of course, the single matrices. So for single matrices, the numerical range is very well known of that. Of course, it has been extended to the multiple matrices. So therefore, you can think about this is really an optimization on this joints of that. So regarding the joint numerical range itself, it's a very well studied. As you can see, lots of people in the operator theory, etc. So I'm not going to get, this is totally another track. But of course, one of the key issues we try to understand is about the convexity of this joint numerical range. Of course, in the MD of equal to the one case, it's just the first only has one of the matrices, and this is a well-known Toeplitz-Hausdorff theory. And then in terms of if you have two matrices of that, and three matrices, and so on. So there's tons of literature and in this particular in the matrices theory, and these people in the core linear algebra field study that extensively. So within this, So now we can provide a so-called geometric interpolation or geometry of this SCF iteration. So what this really does is that, so maybe let's first the formula. So basically you generate a bunch of the XK sequence by the SCF, just solving this linear eigenvalue problems every step. And of course, you correspondingly has these Y vectors. And then turn out is the Y vector is nothing but the supporting plane of this joint numerical range. So in other words, in words, basically the SCF with this entirely process, what it does is that it's try to find this maximum on the boundary of this joint numerical range. So, and of course, and further you can prove if you in a convergence and exactly the optimizer or the solution of this linear eigenvalues overlap between of these two vectors in the sense of the normal direction, etc. Of course, pictorial, we have to draw things pictorial. This is basically what's the explainer, what this algorithm does. So you basically you started with the initial of guess, and then you first the solution gets into the boundary, and then you're looking for the boundary on that. Each of the boundary you have at this point, you have this normal direction, you have this gradient search. So this is the high plane, and then you're jumping from the one point to the next and continue eventually converging to your solution. At this solution point, the gradients and within this normal directions are coincident. So I think this is very exciting in terms of our, at least we feel very excited about the understanding this SCF of this process, because it's quite a sort of amazing in the sense of for this class of the problems, and we can using such geometry. Of course, you naturally will extend into the domain. In this case, if the domain is not convex, etc., and the path we are continuing pursuing is using this convex Hall, etc. So doing that type of that. So this is basically the first answer to the first questions of that. What's the geometry of this simple of SCF iterations? So in this problem setting, they are looking for around the boundary of this convex domain, and until we get to the convergence points, etc. So of course, within this geometric illustration or geometric domain is naturally inspired us to be able to rigorously prove this global convergence of that. So this is a sort of you might call it observed and also rigorously proved, and be able to show that this SCF settings and its globally convergence, you guarantee the so-called monoticities of the solutions, and also at the convergence point. In other words, at this point when the normal direction with gradient direction coincide. So at this particular point, you can prove the optimality of solution among all the sequences of that. So therefore, this is a very rewarding experience in the sense of we push ourselves to understanding this simple SCF iteration, what's the geometry of this type of iteration, and it leads to a very surprising and rigorous proof about the convergence of such a seemingly simple recursion of that, etc. Okay, so this is my last series. And then, so of course, in addition, we also can pursuing this local convergence, etc. And also, of course, in practically, we not only do the simple SCF iterations, we're doing this so-called accelerated SCF, because you can using the field previously computing the XK and to get to the accelerated procedures, etc. So one well known is so-called Anderson acceleration, etc. And David Keys, etc. In the audience, he knows more better than I do. But practically, you can incorporate all this. So, so for the rest, probably 2 minutes or so, I give you an example. So this is example of that is a so-called quadratic maximization. As you can see, each of these functions is just simply the quadratic of this xk functions. So of course, now you naturally think this is problems can be equivalent to nonlinear eigenvalue problems like this within the matrices of this form. And so the world probably the simplest, the most well-known problems is so-called numerical radius calculation, which has tons of the need. If you're looking at of that Nick, the pseudo-spectrum book, etc. So you find that it's a very fundamental quantity to understanding the behaviors or transient behavior of an operator. So therefore, if you're rewriting this numerical radius, and it turns out it's the optimization as we just talked about, and also we need to find a solution on a complex domain. So so there's a lot of algorithm. So in that, we really talk about dozens work being published on this. But of course, relatively very few algorithms being developed to how to develop algorithm, extending those algorithms, or how to computing the numerical radius of joint operator, because this is directly connecting to the problems such as the simultaneous diagonalization, etc. So you need to developing of that. And of course, for now, under this setting, it's really we can unify of both of that. It doesn't matter you compute a single matrix radius or you computing a set of joint matrices of radius, etc. So really provide a uniform treatment. Okay, try finishing that. So here is an illustration. Again, for this problems, we're using little matrices. That's illustrating this shaded area. Is of a joint numerical range, and then if you have all different starting vector, is each of the color you divide of that, because for these problems, so there is a 3, or at least the numerically it proved illustrating there's a 3 local maxima. So therefore, you're starting from the different starting vector, you're converging to different of a local maximum. And this is just to show you of this standard SCF, and then we also have accelerated SCF, etc. But that's no time to talk about. But I really show you that this is you're starting with this, the algorithm rapidly converging to different of that. So typically, to solve these problems, you will first find a local maximum, and then you through this so-called globalization, you do the certification of a global optimizer, etc. So the tool we developed here is really provided of a treatment to all this locally. So, and of course, more generally, for example, people doing this, so Hamiltonian systems, and they're doing you can formulate this as of 3 matrices too. And then it's, of course, the domain is more like a potato shape. And then what this algorithm really does, you starting the vector and it converges to a domain, and you can use reading of that, etc. So I'm sorry, really rush of that. So in the sense of that, so if you're interested, of course, the paper we just posted on the archive, and also all the numerical example here is the code is over there. And of course, today I'm going to talk about a single vector cases. Each x here is vector. Naturally, you're asking what's the bunch of if you have a clock case. And also, the other direction is that this nonlinear eigenvector approach and how this will be arising in other types of optimization, etc., particularly on the optimization with orthogonality constraint. So this is, for example, in the Wasserstein discriminant analysis, etc. It turned out you can all reformulate it as a nonlinear eigenvector problems, and then subsequently of solving them using a much more efficient numerical linear algebra solvers, etc. Okay, yeah. Finally, this is doing advertising. I don't have time. Alan, pursuing that. This is another very exciting work, and so hopefully it's not much citation yet, according to the Google Scholar, but I'm pretty sure back to the years to come. This is really a very, very exciting to illustrating it's a 20 years old open problems. Finally, Alan nails down and just published in the Science. Okay, thank you. I'm sorry.
Yeah, we'll take only one question.
Really quick,
you really.
So
So I found, while you were talking there, I found Alan's 1980 high school yearbook photo. Yeah, I emailed it to you.
Okay, oh, wonderful. Yeah, that's exactly. I was Googling the classmates.com. They asked me to pay. I said, forget it. Wonderful. Yeah, it's very impressive, I think.
Okay, so let's thank Zhaojun.
Yeah.